High temperature applications. To address the constraints of high temperature applications for DHW and retrofits, where legacy hydronic systems were designed for 80 to 71 degrees C cycles, the choice of refrigerant and system architecture are key considerations. Standard synthetic refrigerants such as R32 and R454C are generally limited to 60 and 70 degrees C respectively at -5 degrees C ambient temperature. Reaching higher temperatures requires specialized natural refrigerants such as carbon dioxide or CO2 or bivalent or cascade system configurations. Refrigerants at higher critical temperatures such as propane or R290 and ammonia or R717 are generally better suited to medium and high temperature heating applications because they maintain efficient subcritical operation at elevated condensing temperatures. This allows stable production of low temperature hot water or LTHW flow temperatures in the range of 65 to 80 degrees C, supporting retrofit projects where existing terminal units may not be oversized for low temperature operation. In contrast, CO2 or R744 operates using a transcritical cycle and is particularly effective where very high DHW temperatures are required. Although capable of delivering water temperatures above 80 degrees C, system efficiency is highly dependent on return water temperatures and hydraulic design. CO2 systems therefore benefit from large waterside temperature differentials and are commonly configured for dedicated DHW generation rather than general space heating. CIBSE Journal CPD Modules 263 Transcritical CO2 Heat Pumps for Commercial Buildings considers transcritical heat pump applications in more detail. A refrigerant's thermodynamic characteristics directly affect hydraulic strategy. Lower flow temperatures generally require increased system flow rates to maintain heat output, potentially increasing pipework sizes and pump energy. Conversely, refrigerants capable of higher temperatures may be more appropriate for retrofit applications, but can reduce seasonal efficiency if operated continuously at elevated condensing temperatures. For many commercial applications or multi-residential developments, a cascade heat pump configuration is often the most versatile option. This involves placing two heat pumps in series to divide the total temperature lift. A primary air source unit produces low temperature water, which acts as the heat source for a secondary water-to-water unit. This arrangement can be used to provide high temperature DHW or to lift the supply water temperature in steps on a fifth generation heat network, for example. This cascade arrangement reduces the pressure ratio across each compressor, protecting the equipment and improving overall efficiency. It is particularly useful when a building has simultaneous requirements for low temperature space heating and high temperature DHW. One unit provides the low temperatures, while cascaded unit independently boosts a portion of the water. The efficiency of these two systems is determined by the ratio of the total useful heating-cooling output to the total electricity input for all heat pumps in the series cascade system. This overall COP for the system can be calculated from the COP of both heat pump stages. Implementing a cascade system presents a specific engineering challenges. First is capacity balancing, because the secondary water-to-water heat pump contributes compressor heat energy to the final output. The primary external air source heat pump, or ASHP, does not need to be sized for the entire building load. Often 75% is sufficient. This manages plant footprint and reduces capital costs. Second is the management of defrost cycles. During cold weather, an air source heat pump must periodically reverse its cycle to clear frost. To ensure continuous heat delivery and prevent the secondary heat pump from drawing in excessive cold water during this phase, a buffer vessel is often installed between the two stages to prevent system inertia. In retrofits where electrical capacity or budget is limited, a hybrid or bivalent system may be more appropriate. This pairs an undersized heat pump with a retained gas boiler. In partially parallel mode, the heat pump preheats the water and the boiler provides the final temperature lift. In switch mode, the system transitions entirely to the boiler when ambient temperatures fall below a bivalent point, where the heat pump can no longer meet demand efficiently. Hydraulic decoupling via a low-loss header is essential in these setups to prevent high-temperature boiler water from returning to the heat pump and causing safety lockouts. CIBSE Journal CPD Module 205 Bivalent Heat Pump Systems for Heating and Hot Water and 251 The Pros and Cons of Various Hybrid Heat Pump Heating Systems provide more detail on hybrid heat pump systems.